In this video, I'm going to try to provide some additional insight into the results of your current and voltage investigations that you carried out both yesterday and on Friday. I want to start with a quick recap of the current experiments that we did. So, pretty typical measurements would have been for 0.3 amps there, 0.2 amps, 0.1 amp, and the same over here, like this. And from that data, many of you could see something like this. The current in the branches of a parallel circuit add up to the total current in the circuit, or the current from the battery is distributed to each branch. Those can be sort of more generally worded as to say that the current coming into a junction, 0.3 amps, equals the current flowing out of that junction. There's 0.1 there and 0.2 there. So again, whatever current we have flowing in flows out of that junction also. In the series circuit, the data look more like this, with the obvious conclusion that the current at any spot in the series circuit is the same as any other spot. And it turns out that these two things really say the same thing because of of course there are no junctions there. And in either case, the current in any branch depends on the resistance and the voltage across the branch. Now, an interesting question could be asked, well, why is it like that? We can see that it's like that. We can have a rule, but why is it like that? It turns out that both of these rules actually are consequences of the conservation of charge. That is the idea that charge can't be created or destroyed. And since current is just the rate of charge flow, so we'd expect that no charge would be destroyed in the circuit. We may remove the energy stored in the wires thermally rather than electrically, but the charge itself doesn't go away. So again, both of these rules are consequences of the conservation of charge. Now let's flip over to the voltage side of things. This was the investigation yesterday, and most of you found that the voltmeters here read about 5, 5, and 5. May not have been what you predicted, but few of you expressed much surprise or wondering about that. On the other hand, the meters here read something like this, and this was a bit more puzzling. So I want to give you two perspectives on why it actually shouldn't be very puzzling to you, though certainly I expected that it would be puzzling to some of you. Let's use our definition of resistance to see that with a 50 ohm resistor, the current here and here is going to be the same because it's a series circuit. And we saw in a series circuit, no matter where you are in that circuit, the current will be the same as any other spot. So the I for the two resistors will be the same. Let's write out that same thing for the 25 ohm resistance. Remember here, that and that are the same value. So if the resistance is bigger here, the voltage must be bigger, as we see. The resistance is smaller here, the voltage must be smaller, as we see. Now, if we had exact current measurements, then these voltages we would calculate here would be precisely the values you read on your meters. So we can see from the definition of resistance that it should be this way. But that doesn't necessarily explain why it's that way. So for that, I want to flip over and I'll redraw these voltages in here. And then we'll come back in the second segment and talk about why should it be that way. Get those voltages right.